So our next speaker is Michaela Campanello, who's going to be talking about Vegas.
Good morning. As you see from the title of my presentation, I will give you a brief overview of the VST Vegas survey and focus more on the results that we obtained and just recently published on small cell systems. The survey is a GTO with maximum capacciore SPI, and here's a list, I hope it's quite complete, of collaborators, Italians and from abroad. Okay, VEGA stands for VST Survey of Elliptical Galaxies in the Southern Hemisphere. It spans on over about 5 years. We will have, for all targets, about 110 bright elliptical galaxies, G and I, deep G and I observations. For most targets, we will also have R-band, and for some selected targets, U-band will also be obtained. These are the specs of the survey. Some targets will be overlapping with kids. In general, we expect to have 3 hours integration total for each object. The data reduction has already been said for other surveys is carried out by using VST tube. This is part of the targets that have already been observed and reduced. Main scientific aims of the survey are light distribution to very large effective radii thanks to the field of view of the imager, study color profiles, SPF magnitudes and colors, and obtain very quite complete census of satellite systems. So, in the following slides, I will concentrate on this part of the study that we have, as I said, already started and something has been published. So, what I mean with small cell systems, basically, with this term, we refer to global clusters, extended clusters, UCDs, I mean, a zoo of bright and compact objects that live in the neighborhood of bright galaxies. And okay, I promise with what goes on and back. Okay, live in the potential well of the bright galaxy. Why we care about them? Because, well, first of all, they are very numerous. Then they have a population that is much less complex with respect to the host galaxy. We heard from Gianpaolo a couple of days ago that actually the population of by these systems is not as simple as we thought some years ago. However, it's still much simpler than the population housed by the galaxy. So it is quite easily interpreted in terms of a simple stellar population model, so to constrain the properties of the object observed. These objects are relatively easy to detect out to very large distances. This is I wrote 100 megaparsecs, but there are observational global clusters out to 400 megaparsecs and more. And the properties of these objects, which are, as I say, relatively simple, are fundamental to constrain information evolutionary scenarios for the host galaxy. So, however, as I said, the main body of the biggest survey will mostly rely on one color observation, the G and I. The problem with this kind of data is that you have just one color. This is a color magnetic diagram of all sources in one of the biggest field. As you see, using one color in the color range expected for satellite systems, you have a huge contamination from foreground stars within the Milky Way and background galaxies. Having a further color of the R-band using the R-band observations will significantly help in reducing this contamination, but the great step forward is when you have U-band also, at least. As you see here, this is a preliminary result from the field NGC 3115, that the global cluster population, which is almost, the color range is the same as for UCBs and other satellites, lines up in a very well-defined region. So the level of contamination using U, G, and I color diagrams drops to levels that go from about 50-60% and more to 20% or even less than that. Probably in the best cases will be using these two colors 10% contamination for and background. The ideal case would be having also K-band, some near-infrared color. This is something that has been recently demonstrated by Munoz et al. Using NGVS and GVS IR data, that if you select objects within this region, the level of contamination that you get is about 5%, so it's very small contamination. Nevertheless, we started from this galaxy, NGC 3115, and showed that thanks to the properties of the telescope and imager, we still have a great chance to analyze the properties of small stellar systems very accurately. In particular, we have followed two different approaches. Although for this galaxy, this is again, and this is 3115, we already have U-band observations, so to make a very a better constraint, to obtain better constrained colors, we use only two bands, G and I, and in particular focused on the G-band observations to try to study what kind of signs one can get out of this kind of data based on just two colors, two filters. So thanks to the very large format of the imager again, so this is, the black dot is the galaxy, and it's the radius here, the black region is about 4 effective radii of the galaxy. The gray elliptical annuli reach about 23 effective radii. So I hope you see them. We go very much to the outskirts of the galaxy somehow. And the background you see here, the red dots are what we assumed as a background. So by very simply subtracting the surface density of objects from the inner and the outer regions, we obtained what we obtained here, the density of sources within the inner regions. This is the background density, and by subtracting the inner to the outer density, we obtained the density, surface density. This is shown versus color. I'll show you in the next slide, versus magnitude. So the power of the method stands here, as you see here in this histogram. There are quite obviously two peaks in the color distribution. Different curves refer to the color distribution to a larger and larger radii. So the histogram is in the inner 4 arc minutes, and then smoother curves and shallower too we are going to other larger radii by analyzing the the color distribution. By analyzing the color distribution, we, for example, obtained the radial color profile for the blue and red peaks, and you might see here there's a shallow gradient, which is something that you expect. But more than that, I want to point out here the fact that, as you see here, there are black dots and gray lines. Those are similar results obtained from Subaru and Keck, 8-10 meter class telescopes. So this is showing us that with this kind of approach, we can reach very large galactocentric distances and accurately study the property of this object. And well, I'm going in the wrong direction. Further results: the density of globular clusters versus radius. The black is the total density, blue and red are the blue and red clusters. As you see, the comparison with the galaxy light profile with arbitrary scale shows a very good matching with what we expect as a Doppler profile. I mean, there's a lot of things I should say, but I just want to go quickly to the conclusion. This is the luminosity function, again obtained in this, using this background subtraction technique. The inner density, the background density, the difference between them, and as you know from the globular cluster luminosity function, you get a very reliable, quite reliable distance indicator. We derived that distances. We were not much interested in that, but more than this, we focused our attention on the possibility of inspecting how the turnover magnitude of globular cluster GCLF change with respect to the radius, and we basically found that, again, thanks to the large format of the imager, there is no change in the turnover magnitude when you go to large radii. On the contrary, inspecting the blue and red population, we found something that is somehow predictable, that the difference of the position of the turnover magnitude for the blue and red clusters. As I said, one possibility is to study the population using background decontamination. A further possibility is to analyze sizes of the objects. This possibility is clearly depends on the distance of the object. So for the we found basically that for almost given the specs of Vegas, we expect that for almost all the galaxies in the survey, we will have effective radii, will derive effective radii for all objects more extended than UCDs. And this provides you a further physical quantity to constrain and to select the candidates. And well, I have no time to say that, but just this is a comparison magnitude versus effective radii, our results with ACS. I mean, the point here is just to say that thanks to this further physical quantity that you can use, the level of contamination can be, even with one single color, can be lowered to 30% and even less. And these are my conclusions. I would just mention this that was yesterday said by Magda Arnaboldi. This is an optical survey, and it's perfectly, it's ideal case to be complemented with near-infrared similar survey. Thanks.
Do you have any questions for Michaela? Can you say a bit about how you measure the sizes, what software you're using, and I mean, do you find it wavelength dependent as well? Do you worry about it?
Yeah, I mean, we derive sizes using well-known tools, iShape. It's developed by Soren Larsen. It has been tested in different over different objects in different environments. Yes, there should be a wavelength dependence. Clearly, the level of detail that we have does not allow to find this kind of dependence. We expect that once we have a complete census and the complete coverage for each object, that for the most extended objects, I mean from UCDs on, so compact ellipticals, the dwarf ellipticals, and so on, these kind of characterizations will be done. We haven't done that yet.
Okay, any more questions? If not, let's thank Michele again.
Our next speaker will be Paola Luzzi. We'll be talking about the Shapley Supercluster Survey. So you've got 12 minutes, I'll give you 3 minutes.
Okay, thank you. You are going. No, just a minute. Okay. Yes, I know. Thank you. Okay. I will give a brief review of our multi-band survey of the Shapley supercluster. First, I would like to introduce the colleagues involved in this project, in the different aspects of the project. With respect to the field of our investigation, we want to address one of the most debated question in extragalactic astronomy, which is I use this because it works, the role of environment of galaxy evolution. In low-Ehrlich clusters, the dominant populations consist of early-type passive galaxies, while in the field star-forming spirals prevail. But galaxy clusters were not so inactive as at the present epoch. Let me mention the Bachelorman effect, with the blue galaxy fraction increasing with the redshift, and the recent results of Spitzer and Herschel, which observe an increase in the star-host galaxies at redshift up to 1. This trend can be due to the cosmic decline in star formation of field galaxies, but even accounting for this decline, we observe a sharp reduction in the total star formation rate in clusters since redshift 0.3. So empirically, clusters accrete galaxies, star-forming galaxies from the field, and transforms these galaxies somewhere, somehow, in the early type passive that populate the clusters. Several mechanisms have been proposed to do this work: the tidal and gravitational interaction, hydrodynamical interaction, and other processes like starvation and preprocessing. But it's very difficult to disentangle among these processes to understand which one is working more effectively in a particular galaxies and in a particular environment. And things are even worse, because the galaxies move into the environment, and in the hierarchical universe with assembly of structure, what we are actually observing and investigating is the galaxy evolution in a changing environment. And the prototype of a changing environment are the superclusters, which are dynamically immature, with the clusters and groups interacting, with galaxies being accreted from the filaments into the cluster core. These systems are not only the ideal place to study the cluster-cluster collision, but also the place for the investigation of the role of the cluster scale assembly on galaxy evolution. And also, we can map the galaxy evolution from the filaments to the cluster core, searching for the very first interaction between galaxies and environment, and distinguish between global and local environmental effects. So these are our aims. And so what we know is what we need is only a supercluster, the right one, which is dynamically active, a homogeneous data set from optical band to infrared imaging, and the spectroscopic information, where the galaxies are. For the cluster, we choose the Shapley supercluster, which is the largest conglomeration of Hubble cluster in the universe. It has a very complex structure with main body, walls, filaments, and it is collapsing probably dynamically bound in the central region within 10 megaparsec radius. This is the superclusters, and this is the center that is investigated with the SHAS survey. This is the 10 megaparsec radius. The red dots are the literature redshift of the supercluster in that velocity range. The medium redshift of the supercluster is 0.05, and these are the clusters in the regions. The 23 square degrees VST field covering the whole area, that at this redshift amount to 260 square megaparsec. To show you what is going on in the very center, in the core of the supercluster, I use this intensity, X-ray intensity map, where not only the clusters are detected, but a filamentary structure pervading all the core, which is an unquestionable sign of cluster-cluster interaction. The data comes from VST, A omega, and VISTA. Together with this proprietary data, we benefit of the wise coverage in infrared and mid-infrared, and we already have acquired in the previous years Spitzer and Galax for the center of the supercluster. The optical survey in 4 bands reach a magnitude limit that allows us to determine the properties of galaxies down to m-star plus 6 at the supercluster redshift, well in the dwarf regime. These are the completeness, 100%, and this implies also a reliable star-galaxy classification. This is the present coverage of, with VST. The I band is complete. All these fields, the colored fields, those that are observed, were acquired almost all, the 90% say, with a seeing, a subaxec seeing. Especially in the R band, we have a medium seeing of 0.8, that at superclusters, the redshift means 0.75 kiloparsec. And these are examples of the supercluster galaxies in the magnitude range from m-star -1 to m-star plus 4. And our star at the supercluster redshift is about 15. From this composite image, you immediately understand that we can distinguish the internal feature of the galaxies. So we can make our morphological study, we can classify the disturbed and undisturbed galaxies, and we can also even observe hints of extraplanar emission. And for these galaxies, like that one, with this feature here, we carried out an integral field spectroscopy follow-up with WISE, because only integral field spectroscopy tell you the truth, if this is real and outflowing or it's just a chance alignment. And this is another case with a very beautiful tail of ionized gas. So we know that we can do our morphological study. We need to know where the galaxies are. And so in 2013 we carried out a spectroscopic survey with A omega. covering almost all the area with 14 A omega field. We increase the redshift quite significantly, and also we increase the supercluster set one. But above all, this was the first survey of the supercluster that was designed to be complete in magnitude. This is the improvement in the redshift, and this is the distribution of the Shapley galaxies across the field. The VISTA survey started last year. We covered the south, and we want to finish it next year. So from one side we have the properties of the galaxies, and that we can measure with our beautiful data, and the other side we have we need to characterize the environment. We do this with different environmental indicators, and we start exactly with the characterization of the environment. Using the supercluster galaxies, we model each galaxy with a Kelsen kernel, normalized by the weight parameter accounting for the spectroscopic completeness, and weighted by the W1 with the W1 flux, which is a proxy of the star formation, of the stellar mass. Sorry. This is the map across all the field. The first thing that you see in this map is that all the clusters are embedded in a common network. The other thing is that in the center, in the core, you see practically a continuum population of galaxies. In this core, we have always a flux greater than 315 milliJoule per square degrees, which can be calibrated with the SDS stellar mass and translated into this stellar mass per square degrees. Assuming a depth of the supercluster, you reach a density mass about 10 to 10 solar mass per cubic megaparsec, which is 40 times the cosmic total stellar mass density computed derived by gamma. So quite crowded. We can recover the structure already known with this map, and also suggest other substructure in the cluster, in the supercluster. But most importantly, we have identified this filament 7 megaparsec in projection, connecting the cluster 13559 to the supercluster core. This is a strong support to what was suggested but not clearly demonstrated by numerical cosmological simulations, that the cluster here is bound to the core, to the analog structures. The last view graph, the dark matter distribution that we plan to measure for the cluster in the survey. We start with the very center, containing 2 clusters, one rich and one poor, and this is the map. In the map, the white contours are the dark matter distribution, which can recover, can identify the 2 peaks of the 2 clusters. We also measure derived the mass of 3558 from the Michelson analysis performed by Nobuhiro Okabe, and also can compare it with the X-ray mass of the same clusters, which turns to be consistent. So VST, Capaccioli VST, can allow us to inspect in very detail the Shapley supercluster galaxies and to derive the dark matter distribution. Thank you, and then with the summary.
Do you have any questions? maybe I can just ask, are you planning to do both this decomposition as well? You talked about morphology, but you didn't actually mention decomposition.
Well, we want to use a non-parametric, for all the survey, we want to use a non-parametric approach using CAS plus Gini20 and other indicators. But we want also to use the bulge disk decomposition for the analysis which are bright enough and resolved enough to do it.
My guess is you might see more signatural changes with just the disk component alone than the whole global measurement of the system. Anyway, I should pass on to the question again.
Yeah, first of all, it's not to me to tell, but it's an incredible data set. My question is about the Dark distribution. So you showed it is map, which is rather on a large scale. Do you have any chance to have also a map on a smaller scale?
So, yeah, the problem with the dark matter distribution, I mean, to do these things at this redshift, you have to be very, very careful in the background subtraction, as Okabe taught me. And so what we expect that going further using all the data, we will do this better and we will improve the accuracy. But I don't think that we can have a resolution that is higher than the poor clusters. I don't think so. I mean, at least now.
Okay, let's thank Paolo again for the talk. So our next speaker is going to be Maria Teresa Botticella. That's going to be talking about the SIDARE server. So you have 12 minutes.
First of all, I would like to thank the organizer for the opportunity to talk about the preliminary results of SUDARE survey. SUDARE is for supernova diversity and rate evolution, in collaboration with a lot of people from different institutes. I cannot mention all, just Lino Grado, Luca Limatola, Capaccioli, Codone Vaccari, and Camillo Schifani from Naples. I will briefly present the goal of our survey to probe supernova progenitor scenarios through the simultaneous analysis of the supernova rate as function of time, cosmic time, and in different environments in a galaxy sample. I will detail the two main parts of our survey, the supernova search and the analysis of the galaxy sample we monitored, and I will present our very preliminary results. There is a general consensus that supernovae type 1a are from carbon-oxygen white dwarf, but we still don't know the evolutionary path that lead a white dwarf to reach the Chandrasekhar mass and explode in thermonuclear runaway. In particular, there are two main proposed scenario, the single degenerate scenarios where the companion of the white dwarf is a red giant or subgiant, and the double degenerate scenario where two white dwarfs merge after orbital shifting. In the last year, there are some observational evidence of the coexistence of two different channels for type 1a supernova progenitor, prompt and tardy, and seems also that the supernova type 1a diversity is related to the age of the progenitors. But the question is still debated. And also the picture of the death of massive stars is still unclear. There are several subtypes of core collapse supernovae, and a sequence of progenitor system with higher mass has been proposed with different mass loss histories that go from
type 2 supernovae to stripped envelope supernovae, where the mass loss history is the key factor of the evolution. But more and more observational evidence suggests us that there are some other key factors in the evolution of massive stars, as metallicity, for example, and or rotation. And we still don't know the exact mass range of the different core collapse supernova subtypes. Finally, the new era transient survey are discovering a lot of new supernova types. I just mentioned the ultraluminous supernovae, ultra-faint supernovae that seems from massive stars, a star with mass higher than 8 solar masses, that can be explained with different explosion mechanisms. There are several suggestions: Paris stability for ultraluminous supernovae or electron capture for ultra-faint supernovae, and also very fast type 1a explosion that can be from completely different progenitor with respect to canonical type 1a. There are two possible approaches to constrain supernova progenitor. One is based on the study of single events, for example, with a direct detection of the progenitor on the pre-explosion images from HST, or the hydrodynamical modeling of the supernova photometric, spectrophotometric evolution, or the analysis of supernova remnants. But this approach is possible only for nearby events. There is a statistical approach that studies a supernova sample and the characteristics, the relation of the supernova sample with the parent stellar population, and we do it in the local environment of the supernova or in larger sample of galaxy or in a cosmic volume. Due to the relation of the supernova type rate with star formation rate, we can constrain the delay time distribution of the progenitors that means the age distribution of supernova progenitors, and for the relation of core collapse supernova rate with the ongoing star formation rate, we can constrain the mass range of progenitors. So supernova rates are a very important tool to constrain, to investigate supernova progenitors. The aim of SUDARE is to monitor 4 square degree in 4 different seasons, and 1 square degree in several different periods, collect about 200 hours divided on GTO time and Chilean time, with a cadence of 3 days in R band and 10 days in GN band, and with an exposure time of 30 minutes for each single epoch, with a very good seeing and scale condition. This is the distribution of the magnitude limit of our image, very deep, and the good quality seeing that we can obtain with our requirements. The scale field that we are monitoring are the Chandratic field south. We have 4 different pointing to cover 4 square degree in optical band from SUDARE, in U band from voice survey, and in near infrared from the video survey. We also collected Galaxy Spitzer data that we published last year. The Cosmos, also we are monitoring 1 degree around Cosmos field in optical, and for the Galaxy catalog we are exploiting the UltraVista catalog published by Nuzzi et al. And last year. Here the distribution of the number of filters available for our galaxy, for Chandratic field south and for Cosmos. Here flowchart of the supernova search pipeline is a real-time detection pipeline. The pre-reduction and coding of images is done here with a VST tube. We implemented a pipeline for the transient detection that cover all the steps from the different image to the photometric typing of supernovae. This pipeline is based on Python and PyRAF, OutPants, Extractor. A lot of software is in our pipeline. Here the supernova search is done on VST R-band images. An example of a small piece of images where you can see the wide field of VST can allow us to monitor in one shot thousands of galaxies
and detect rare transient as supernovae. We found in each epoch thousands of the transient sources on the different images. The majority have spurious detection due to cosmic ray or artifacts on the images, but we also detect some moving objects, a lot of AGNs and variable stars. We classified these objects based on their erratic light curve, or some typical light curve of variable stars. And finally, we found about 10 supernovae for each epoch, possible supernova candidates. Here you can see the search image, the template image, and the supernova candidates on the different image. For the supernova candidates, we checked all the detection for all the seasons. And we performed a forced photometry on the supernova position in all epochs and for different bands to obtain the light curves, and used this information for the photometric typing. Here a fit with a template light curve, and this fit allows us also to have an estimate of the extinction and explosion epoch for each supernova. Some example of supernova captured at the maximum, before the maximum, and after maximum peak. In the first 2 years of our project, we detected about 100 supernovae, half type 1a and half core collapse. This is an important point because SUDARE is the only ongoing supernova survey focused only on supernova rate measurements without any cosmological analysis, etc. So we don't have bias about supernova types in our search. Here the distribution of redshift for type 1a supernovae that are more luminous, so we can detect type 1a supernovae up to redshift 0.8. For type 2 supernovae that are lesser luminous, we are at maximum around 0.4. And we restrict our analysis to the supernovae within this redshift range. To calculate supernova rates, we need several ingredients. The detection efficiency, we have to assume dust extinction distribution for the supernova, etc., etc. I don't have time to give you all the details. For the galaxy sample analysis, we used a different pipeline. For the source detector, the galaxy detection, the images, the set fitting, we used easy. Also, we estimated the star formation rate, the mass for each galaxy. We detected galaxy on K-band, deep K-band images of B star. Just example, we have again thousands of sources on our images. We selected galaxy based on a diagram, color diagram, and we select all the galaxy brighter than 23.5 magnitude, about the 90% of completeness limits in this redshift range. The test of the photometric redshift versus spectroscopic redshift for Cosmos and Chandra deep field south. The difference is due to the different number of filters, the distribution of the photometric redshift, and the red spray color that allow us to separate passive and star-forming galaxy in our sample, the distribution of the mass, stellar mass in our galaxy, and the star formation rate. You can see are very similar in both fields. And finally, the identification of the host galaxy of supernova sample. Only in the 10% of cases we have host galaxies that are too faint and are not in our galaxy sample, so we have to discard this supernova from our analysis. The recipe to calculate the supernova rates in the galaxy sample, we need to normalize the supernova rates per unit mass in this case, so we need to know the galaxy mass and also to apply a correction for the incompleteness of our magnitude limited sample. Here the first results, the core collapse rate, a redshift 0.3, and type 1a supernova rate in 3 different redshift fields. The core collapse rate are in good agreement with the previous measurements. For type 1a we found higher rates in all beams. We checked all the systematics in our analysis. At the moment I can just confirm these results. We also studied supernova rate function of the specific star formation rate. And also in this case we see
I expected dependence of core collapse supernova rate on a specific star formation rate that is expected because core collapse rate is strictly correlated to the ongoing star formation rate, but also unusual increase of supernova rate in starburst galaxy. This information point out toward distribution of the delay time for Tapanei supernovae with a larger fraction of young progenitors. Now we are analyzing the dependence of supernova rate on stellar mass. We have to put all these information together to have to compare the expected observed supernova rate and okay, these are our preliminary results. This is a work in progress. We also plan to measure the supernova rate in galaxy clusters that are in Cosmos 800 deep south, and also the supernova rate as a function of radioluminosity and metallicity. Finally, we have to analyze the data we are collecting in the last 2 years of the survey. Thank you for your attention.
I'm curious whether the slightly higher supernova 1A rate could be consistent with the cosmic variance or the sample variance.
We checked also the cosmic variance, and it's interesting. We found agreement with the rates measured by Dalen on the goods field with HST. Sorry, is this one that are the highest. So looking the supernova rate in galaxy cluster, we can have a cross-check about the cosmic variance.
And these areas, these areas don't include the cosmic variance, or those?
No, include the cosmic variance.
Okay.
Related to your comments, you
Yeah.
have very low masses, which are not going to be perhaps the total mass of the galaxy. And I wonder how this settling this enhanced supernova rates.
Yeah, the distribution of the mass in both fields seems very similar, and we also performed the same estimation with a different parameter WISI, that is the photometric Monte Carlo redshift.
I know that code. It's
Yeah.
not very physical because it's doing PCA
Yeah.
instead of getting the properties of galaxies.
Yeah, the idea is in the future to collect more Spitzer data and estimate the star formation rate and the mass by using the luminosity, the infrared luminosity, UV luminosity, and combining. So with a different probe of mass and star formation
Yeah,
rate.
because your
But at the
picture
moment,
studies the line.
at the moment for supernova rate, these are the estimate that people use it for mass.
Yeah,
The previous work,
it may not be the supernova, it may be your underlying stellar mass and star formation rates that need to be revised.
Yeah. I agree.
Okay, we have one question over here.
For any of the objects in the sample, is it possible to go after progenitors, individual progenitors for any?
No, because the direct detection,
Yeah.
no, because it's possible only on HST image with a very, no.
So you don't intend to try and...
No, we have just a statistical approach. We just are studying the age distribution on all the range we are monitoring, not for each single object. There are some kind of study with mouse that are doing this, but I don't think that the star formation estimate for each galaxy is so better constrained that we can do this kind of analysis. This is my subjective opinion.
Okay, last question today.
Can you say more what you concluded about the delay time distribution, what you were saying at the beginning? So the type 1A rate seems to be declining pretty steeply, which
because
seems dominated by prompt.
Seems that our results can give in this direction. But the next step of our work will be to, I will show you some example, to take some double degenerate, single degenerate model, combine it with some star formation history, and see the agreement with between predicted and observed supernova rate. So we are working on this with Laura Greggio and other people in Padua, and but the first result seems to prefer high fraction of prompt objects. Yeah.
Okay, let's thank Maria Teresa again.
Thank you.
So we break for coffee now, and if you go